This question is about three amines. Remember, an amine has an N in it. This one's a primary amine, this one's a primary amine, this one's a secondary amine. Primary amine, the N is bonded just to one carbon, N just bonded to one carbon, whereas this N is bonded to two carbons, this carbon here and this carbon here. So we've got two primary and a secondary amine. They're weak bases, so remember what a base does. A base reacts with an acid. Acids make H pluses and bases react with the H pluses. So which ones of these are weak? Well, they all seemingly are weak bases, so they're not reacting with acids readily. Explain the difference in the base strength of the three amines and give the order of increase in base strength. So why might each of these react with an H+? The reason they react with an H+ is because there's a lone pair of electrons on the N. The question is, how available is that lone pair of electrons? You could think of it how large it is, how much of it is there, but we say how available it is. Well, on this E, the lone pair of electrons is withdrawn into the ring. A ring will withdraw electrons into it. So the availability of the lone pair of electrons on that NH2, with it being so close to a ring that's withdrawing the electrons, is very small. So if that's not very available, then it's not available to bond to an H+, and that's going to be a very weak base. This one, however, is a long way from the ring, and so the electrons from this won't be as withdrawn as much, and I've got CH2, CH3. Like methyl groups, they'll push electrons away from themselves. CH2s and CH3s even more so push electrons away from themselves, and so that's going to be more available on here on this nitrogen. There'll be a more available lone pair on that nitrogen because the lone pair is further away from the ring, and we've got CH2 groups pushing electrons onto the N, so that's more available, and that's going to be a strong base, the strongest base of them all. And this one's somewhere in between. It's got an N right next to the ring, so that's going to withdraw, but it's got a CH2 and a CH3 that's going to repel electrons and make it slightly more available. So this is somewhere in the middle. So let's actually have a look again then. So the N on the lone pair reacts with an H+, acts as a base. We've said that the ring withdraws electrons into the ring. We've said that the delocalization into the ring lowers the availability of the lone pair. Delocalization means just pulling or withdrawing electrons or moving electrons. The delocalization into the ring, moving the electrons into the ring, withdrawing them into the ring, lowers the availability of the lone pair. Yes, we've said that, and lowers the base strength. Yes, so if it's less available to bond to an H+, and it's a weaker base. The nearer the N is to the ring, the weaker the base, and the CH2, CH3 repel electrons and increases the availability of the lone pair, increasing F and G base strength. And so the order is least available lone pair, weakest base, most available lone pair, well away from the ring, and I've got a CH2 repelling electrons onto the N, making it more available. So lone pair to bond to the H+, and then G somewhere in the middle.